So, our speaker today is Julian Kranz from the University of Münster, and he will talk about K-theory of non-commutative Bernoulli shifts. Please, Julian, go ahead.
Yeah, thanks a lot. Thanks a lot for inviting me to the seminar. So I'll talk about a project that we did with Chakraborty, Echterhoff, and Nishikawa. So we calculated K-theory for some things that can be called non-commutative Bernoulli shifts, or I mean more precisely for the cross products. And let me start with motivation. So the motivation was to calculate K-theory of the wreath products. So if you have two discrete groups, G and H, then you can form an infinite direct sum of H indexed by G. You can act on this by left translation or by right translation. And then you can form a semi-direct product of this action, and this is called the wreath product. Yeah, so you take the group generated by this infinite direct sum and by the group G, and you introduce the relation that conjugating by G implements the action on the other group. And so these are called wreath products. And so the basic example that you might have seen before is the lamplighter group, which is a wreath product of Z mod 2 acted on by Z. And so as I said, the goal is to calculate the K-theory of these of the group C-star algebras of these groups. So the topological K-theory. Maybe in terms of the K-theory of H and the K-theory of G, because of course in general this is hopeless. But maybe if we understand H and G, then can we calculate the K-theory of a wreath product? And so I should say a little bit about the structure of this C-star algebra. So how can you also describe the reduced C-star algebra of a wreath product? So if you just have direct sums, if you just have two groups, and you take the reduced C-star algebra of the direct sum, then you can decompose it as a minimal tensor product of the group C-star algebras. And this you can iterate for larger and larger finite subsets and pass to inductive limits. And then, so you can pull out the inductive limit. So what you get is in the end, you get an infinite tensor product corresponding to an infinite direct sum. And so the infinite tensor product is by definition just the inductive limit of the finite tensor products where you take the inclusion with the unit. So of course you can only define infinite tensor products for unital C-star algebras. And now, I also give you the definition of a cross product. So this is the C-star algebra version of the semi-direct product for groups. So if you have a unital C-star algebra with an action of a discrete group, then the cross product of this action is a C-star algebra generated by a copy of the original C-star algebra and a copy of the group, which is a group of unitaries now in the new C-star algebra, with the additional relation that conjugation by the group is the regular. Conjugation by the group implements the action on the original C-star algebra. So this is a universal C-star algebra which you can just define via generators and relations. But we are, in many cases, we are interested in the quotient of this, which is the reduced cross product. And for this, you can write down some regular representation. I will not give you the formula here, but there's a very standard representation of this thing on L2 functions on G with values in A. And then the image in bounded linear operators of this space is the reduced cross product. And so I guess it's easy to see, at least for the universal one, that the semi-direct product construction translates to a cross product construction, and then for the reduced cross product it's also true. And so in conclusion, we can write this wreath product. We can write it as a cross product of a shift action on an infinite tensor product. And this is called a non-commutative Bernoulli shift. And so I make the goal now a little bit more general. So the goal now is to understand how to calculate K-theory of these cross products for these very specific shift actions. And maybe
may I ask a little question? So suppose H is finite, right?
Right.
So C star of H will be some semi-simple algebras and some of finitely many copies of the matrix algebras, right? And then say G is the integers, and then you take the infinitesimal product, and you get an AF algebra, I suppose, with an action, and you take the cross product. But then you, have forgotten all about H when you do this. So,
like, can you recover H from this? You mean?
Yeah, so what if I get? I would expect, that to get a response, to get an answer of what the K-theory of such a thing is in terms of the K-theory of the AF algebra and something about the group, but not. How can I? Yeah, what does, if you say you are going to give me a response in terms of the group H? It's I don't know. Do you really? Does it really matter what the group H is, or just
not really. I guess so. It only matters what the group C star algebra of H is, or not even that really. It only matters what the what the K theory of the group C star algebra is, more or less. Or okay. I will. Maybe it's easier to explain with the formula in a couple of slides.
Okay,
but it
sorry.
does not depend too much on H itself, but only up to some weak form of equivalence, right? But in the converse, I guess it's this probably loses a lot of information about H. It certainly forgets if H was abelian or not. I guess. So in the converse, maybe that's not so clear what we recover. But okay, so this is the goal. Okay, before giving you the actual formula, I guess I will tell you some strategy on how we will get to this formula and what the assumptions are. And so one of the assumptions that we use is the Baum-Connes conjecture. So we will just use the Baum-Connes conjecture as an input. We will just assume it for all of our groups, or at least for groups G acting. We will assume the Baum-Connes conjecture with coefficients to calculate the K-theory in the end. And so what does the conjecture say? So it's, the version with coefficients is, I guess, to Baum-Connes and Hickson. It says if you have a discrete group, then and a GC star algebra, then you can write down some assembly map which computes the K-theory of the reduced cross product in terms of some topological object, which is, I guess, the equivariant K homology of a universal proper G space with coefficients in A. But it's not too important here what this left-hand side really is, because we'll not explicitly use it. And I will give you a reformulation of the conjecture on the next slide, which we will actually use. But I just wanted to state the original picture or the original formulation. And we will, as I said, we will just assume the conjecture for all of our groups. And there are many examples of groups where the conjecture is established. So, for instance, a-T-menable groups, or groups with the Hagro property is another name. So this is the Hickson-Kasparov theorem. This includes all amenable groups, but also free groups and all sorts of examples. Then hyperbolic groups. This is a theorem of Laforgue. It's important that we have a reduced cross product. And there are counterexamples to the conjecture with coefficients. But I guess so far only there are counterexamples with coefficients, and these groups are very exotic somehow. So these are very difficult involved constructions, these groups, and they are non-exact. So there are still many groups where the conjecture holds, and with trivial coefficients it's still open. Okay, so but yeah, this is the kind of original formulation, but okay, and as I said, we will assume it that this conjecture holds. So there's a reformulation of this conjecture that we will actually use, and it's so this is I mean, we also call it the going down principle, and so this was first a theorem of Chabert, Echterhoff, Yono, that what I'm going to show you here follows from Baum-Connes, and then later Meyer and Nest they actually proved, I mean, in a slightly different formulation, that this property exactly characterizes Baum-Connes. And okay, so the statement is, so you have a discrete group G and it satisfies Baum-Connes with coefficients if and only if the following statement holds. So whenever you have two GC star algebras A and B, and say you have an equivariant map from A to B, or more generally a KKG class. So if you don't know about KK theory, maybe just ignore it and just think about an equivariant morphism. When the statement is, if this thing induces an isomorphism on the K theory of cross products by finite subgroups, then it's already an isomorphism on the K theory for the whole group. Yeah, so this theorem tells you if you have an equivariant map to begin with, and this is important. I mean, you need to have some G equivariant map in the beginning. Then you can test isomorphisms just by looking at finite subgroups.
Sorry, and you do not need any universal coefficient theorem or anything. I mean, just homing in KK on the left with the complex numbers gives it. I mean, you do not need. I would have expected that the first map be an isomorphism in KKA in KK. I mean, so that A maps to B is an isomorphism in KKH for every finite group. Okay.
Right. So this
for
would
a finite
be...
group, this implies this because H is finite, I suppose. I mean, the hypothesis implies that the map from A to B is an isomorphism in KKH.
Really?
No, I ask. I mean.
No. So I don't think so. I mean, already even if you have a trivial group, I mean, it could be that A and B have the same K theory, but not. I mean, one satisfies the UCT and the other one doesn't. So this could happen. So we kind of lose information by passing two K theories. So it's not a. So yeah, right. So this will. I mean, what you could do is you could. It could be, for instance, that A and so there is a K theory equivalence, if you want, between A and B, but one of them satisfies the UCT, the other one doesn't, and K theory will not see this. So this could be, but it's but it doesn't matter because we only ask conditions on K theory. I guess the other one would be some strong Baum-Connes conjecture.
Yeah.
Right. Right, but we are only interested in calculating the K theory of a cross product. I guess in the examples of a-T-menable groups, for instance, I mean, we have a much stronger statement in KK theory. Right, but I mean, yeah, this is really the equivalent formulation of the conjecture. All right, so yeah, this is what we will use, and so we will reduce many statements to finite subgroups. And so the strategy will be to use this going down principle to calculate the K theory of a Bernoulli shift by replacing the algebra, the coefficients, by some easier to understand coefficients. And I will and then the idea is that kind of we will have A and B which are equivalent in some sense, and then we will need the Baum-Connes conjecture to produce an isomorphism on K theory. But so let me first get into how we get anything for finite subgroups to begin with. And so this is a lemma by Izumi, or I guess, I mean, so Izumi proved this lemma for G being a group of two elements, and when and only for nuclear C-star algebras, but it's really I mean, this lemma holds in general for a finite group and for arbitrary GC-star algebras with more or less the same proof. And so this lemma says that if you have a finite group then now I take a finite G set, but you can just think of the group acting on itself. When this tensor product construction, of course, gives you a functor from C-star algebras to GC-star algebras. You can just take tensor products of morphisms, but on KK theory, this is not so clear if this works. And Izumi's lemma says this does work. Yeah, so Izumi's lemma says there is a functor on KK theory that does the same thing. And in particular, I mean, the only thing which we need to extract from this is if you have a KK equivalence between two C-star algebras, you get a KKG equivalence between these tensor products. Yeah, and maybe one hint why this is not completely trivial, that this is true, is that this map, this will be nonlinear. So it's not so easy to immediately cook it up from universal properties. Yeah, so this will not be a group homomorphism, it's some kind of polynomial thing. Yeah, but it is true, and I mean, this, for example, this can be proven from an explicit picture of KK theory in terms of asymptotic morphisms, where you can take tensor products of asymptotic morphisms and then you can work in the model. Yeah, and maybe I should point out that we do not know, or at least I do not know, maybe people in the audience can correct me, if the same thing holds for infinite groups in general. Maybe with some unitality assumption. Yeah, but so this is so far only for finite groups. But the corollary that we get from this, if we have the statement for finite groups and we assume Baum-Connes, then we get a statement for the whole group and for the K-theory. So assume you have a discrete group satisfying Baum-Connes with coefficients, and now assume really you have a unital star homomorphism between two C-star algebras. If you have this, then you can write down an equivariant homomorphism between the tensor products. And here unital is important because, I mean, these infinite tensor products are defined as inductive limits of unital things. So we have a map from A tensor G to B tensor G. And by Izumi's lemma, we know we get an isomorphism on finite cross products. And then Baum-Connes implies that we get an isomorphism in general for the whole group. And so this is exactly how we will use Baum-Connes as an assumption. Yeah, so if we have a map between two C-star algebras, then we get an isomorphism on the cross product.
So in the case, in the case of when A is or B is a semi-simple. Right. So you cannot, I mean, the obvious morphism that compares it with the sum of copies of the complex numbers, that is an equivalent, a KK equivalence, is non-unital. Right. Right. So what do you do in that case?
Right. So this is in this case, this strategy does not work. So there is a different thing that you can do in this case. But it's, I mean, this is okay. This is a very good example because just start with the complex numbers for A, and then for B, take some matrix algebra. And then in this case, and okay, let me go back here. So, and in this case, I mean, the K theories will not even be isomorphic for at least if you have an infinite group, right? Because so on one hand, you have just the group C-star algebra of a group, and on the other hand, you have a cross product of a shift action on some UHF algebra. And then we will later see, or I guess this for Z action this was already known, and I unfortunately forgot the reference. Then we will see that the K theory is I mean divisible by the rank of the matrix algebra. So you get something like Z adjoint 1/n tensor with the representation ring, or I mean. Yeah, you get a direct sum of Z adjoint 1/n, where n is the size of a matrix algebra. So unital is very important here. But there is a general trick to get to handle finite dimensional algebras. Right. But yeah, okay. So this is only the strategy for unital homomorphisms, and then yeah, some immediate examples. I mean, where we of course use some statements about KK equivalence of certain things. So if you have O infinity Kunst algebra on infinitely many generators, or you take the Jiangsu algebra, for example. I mean, yeah, you can replace these by the complex numbers, because the inclusion of the complex numbers is a KK equivalence. And for O2, for instance, you just get 0, because because the 0 map from O2 to the 0 algebra, you can interpret this as a unital homomorphism if you accept that that the 0 algebra is unital. And if you don't do that, there's another argument which allows you to prove this. Right. So these are some kind of immediate examples. And from this and the result about UHF algebras I will show you later, you get a formula for general strongly self-absorbing C-star algebras satisfying the UCT, just because we have a complete list of these. Right. So let me give you the main result now. So this is in some sense this is an elaboration of the corollary I showed you before, where we now don't have a unital star homomorphism, but we just have a unit preserving KK equivalence, if you want. And so the statement is the following. So suppose you have a unital C-star algebra satisfying the UCT, and assume that the unit splits off in K-theory, so that the inclusion of the complex numbers as the unit gives you a split injection in K0. If you have this, I mean, you can just consider the quotient, right? The complement of this unit. This is, I mean, this is just some. These are two abelian groups, and you can find some C-star algebra satisfying the UCT, which has this K-theory, which you can always do. And you're allowed to choose your favorite model for this. And then the statement is to calculate the K-theory of this Bernoulli shift, you can replace A by this unitization of B. Right, because they are, I mean, under the assumptions that I wrote down, A and the unitization of B are KK equivalent in a unit preserving way. And then, okay, if you have this unitization, then it's not so hard to work out what the K-theory really is, because you can do kind of an infinite distributive law if you want, and then you can explicitly calculate this. Let me give you again some short explanations for this. So UCT, I didn't write down what the UCT means, but this is an assumption about how KK theory and K theory relate to each other, which is satisfied by, I guess, by most examples of nuclear C-star algebras, which we can write down. Conjecturally, it holds for all nuclear C-star algebras, and we will just assume it for our examples.
So just some question about what is in the formula. So first of all, when you write G/fin, you mean fin divided by the left or right or whatever action of G. And what is GF? Is the stabilizer or what?
Right. So right. So fin G. These are the finite subsets of G. And you act on this from the left, just by moving the subsets around in the group. And when you take cosets you quotient out by the left action. GF is the stabilizer of F. Right, there is B plus is unitization, and here on the left where I highlighted this isomorphism in blue, this is where Baum-Connes is used. Right, but so the formula gives you, so what you end up with is, so the convention that I use here is that if you take the empty subset, this is also allowed, the tensor product indexed by the empty subset is just for complex numbers, and then the stabilizer is everything. So you get one group C-star algebra of G, and the rest are all some finite cross products of actions on finite tensor products.
So if, for example, the group is abelian, right? So there is no, the action is by conjugation, I suppose. So the stabilizer is always G.
No, the action is not by conjugation. The action is just a left translation.
But do you still get a subgroup when you translate? I mean, fin G is finite subgroups or finite subsets.
Oh no, finite subsets.
Okay.
It's really finite subsets. Yeah.
It says it's so. It says so there. Yeah. Okay. Sorry.
Right. So it's really finite subsets, and then this is actually quite helpful, because if you have a torsion-free group, I mean, when there is no finite subset that is fixed by the group action. So in the case of a torsion-free group, what you really get is just some finite tensor products, and you get one copy of a group C side of G. And so then you can really use the Kranz formula. Yes. Right. So these are really finite subsets. And if you have finite subgroups, of course, every finite subgroup stabilizes itself. All right. Yeah. So this is the theorem, the general blueprint theorem, and in the rest of the talk now I will try to give you some examples. So yeah, let's move on to wreath products, and I want to verify the assumptions of a theorem for wreath products now. And for this, the strategy is, okay, we just assume that the small group H is a-T-menable, because by the Higgs and Kasparov theorem, yeah, a-T-menable groups satisfy the Baum-Connes conjecture, and a consequence of the particular proof of this theorem, and I guess maybe this should be attributed to two or to both of them, I don't know, but so a consequence of the proof is that the C-star algebras also satisfy the UCT, and the full and reduced C-star algebras are KK equivalent. So this is a consequence of Higgs and Kasparov. And from this, you can easily conclude, because this always holds for the full C-star algebra, you can conclude that the inclusion of the unit gives you a split injection in K-theory for this group C-star algebra. And there is an explicit model of the complement that you can write down. Just take the kernel of the trivial representation, which you can always write down on the full C-star algebra, and then you transport everything to be reduced with this KK equivalence. Okay, and then the corollary is, I just write down the formula here, is that if H is an a-T-menable group, and G is just any group satisfying Baum-Connes with coefficients, some could also be hyperbolic, then we can calculate the K-theory of the wreath product, which we already identified as this Bernoulli shift, using the formula I showed you before. So via this direct sum of K-theory groups of cross products by finite groups on tensor products. And if you have a finite group, so if H is finite, then you can get even more explicit, because then this B can be understood more explicitly. And so this is okay. The next example, and the intersection of these two examples is exactly finite groups. So assume we take as coefficients some finite dimensional C-star algebra. And now I have to impose this extra condition that so I mean, you split it into matrix algebras, and I impose this condition that the greatest common divisor of all the ranks is 1. So they are co-prime. Yeah, and this is important because of the example that we discussed earlier, that if you just take complex numbers and matrix algebras, then there's some problem with unital inclusions. But okay, so assume this for a moment. And this certainly holds for group C-star algebras of a finite group, because you always have a one-dimensional summand. And then there's a lemma, which tells you that in this case, the unit splits off in K-theory. And so this is essentially, I mean, if you write down the K-theory of this finite dimensional C-star algebra, it's just Z to the n+1, right? And if you right, and then the inclusion of the unit gives you, I mean, this gives you kind of a matrix with whose entries are these integers K0, K1, and so on. And then with some Euclidean algorithm tricks, you can show that this condition which I impose exactly guarantees you that you get a split injection. Right, and then the corollary is that if G satisfies Baum-Connes with coefficients, then we can calculate the K-theory of a cross product again by the same formula, where I use C to the n as an explicit model. And right, and then in this case, we can simplify it even further, right? If you have a C to the n tensor products of this and a cross product by G, I mean, you get some nice finite dimensional C-star algebra. I mean, you can decompose this finite set into orbits, and you're going to get some more explicit formula like this in terms of stabilizers of the G action on some finite subsets. And okay, I forgot to put the name here in the slide, but I would just say it out loud. So I mean, this case has been studied by Xin Li before. So Xin Li wrote a paper, I think it was called K-theory of generalized Lamplighter groups, where he exactly computed this case where you have a wreath product of a finite group. And so this was really the starting point of our project, that we read this paper and we tried to see what's going on there. What can we do maybe more generally? So this goes back to Xin Li. All right, and as I also said before, I mean, if G is torsion-free, this gets much easier, because when you don't have any finite subgroups, and when you really just get a copy of a K-theory of a group C-star algebra, and then you get infinitely many copies of the K-theory of the complex numbers. Of course, if now G should be infinite, I mean, for the trivial group, of course, you just get nothing. Okay, so these are some finite dimensional examples. And let me also give you an example which is not finite dimensional, and where you also have something going on in K1. So yeah, suppose you take continuous functions on the circle, and you have a group satisfying Baum-Connes with coefficients, and you want to calculate the K-theory of this Bernoulli shift. Then again, all our assumptions are satisfied. I mean, a K-theory of a circle is just z in degree 0 and z in degree 1. So you can split off z in degree 0, and you can take as a model for what's remaining just C0 of R. Yeah, and then you get this formula. And this can be understood even more explicitly with equivariant Bott periodicity. Right, so I mean, Bott periodicity tells you how to tells you that tensor products of C0 of R are KK equivalent either to C0 of R or to the complex numbers. But there is also an equivariant version of this for nice representations of finite groups on Euclidean vector spaces, and the theorem, or I mean, one implication of this Bott periodicity theorem, I guess by Kasparov probably, is that if you have a representation which is actually a representation not only on a Euclidean vector space but on a complex finite dimensional Hilbert space, then it's just KK equivalent to the complex numbers. So what we can do is we have our finite set. We split it into orbits. If we have evenly many orbits, we can always pair together two orbits and kill everything. And if we have a odd number of orbits, then we just remove all the orbits until we're left with one. Right, so then we get this formula. And so in the case where we have evenly many orbits, we just get a C-star algebra of the stabilizer group. And in the odd case, we just get, I mean, what we get is just what it is. But so this has this can also be formulated in the terms of equivariant topological K-theory of just of this topological space R to the GF with this action. And then this equivariant topological K-theory of orthogonal representations of finite groups, this can also be computed completely. I mean, I don't want to write down the formulas here, but there's a work of Karoubi, for instance, or Echterhoff and S. So this can really be computed. And then a similar example would be if you take a two torus, or you take an irrational rotation algebra, which in K theory I guess looks the same. Then you get a similar formula, but you get, I mean, the more dimensions you add, the formulas get more combinatorial, but there's a similar principle like this. Okay, so now let's move on to this problem. So what happens if we have matrix algebras? Yeah, so in this case, the inclusion of a unit does not split in K theory, we do have KK equivalent things, but we cannot implement the KK equivalence by a unital map. So yeah, what can we do in this case? So the answer is, in this case, we can just, I mean, if we reason for the unit not splitting in K-theory is a matrix algebra, then we can take care of this. So we can always repair the damage done by matrix algebras. And so this is the following theorem. And so there are two slightly different statements which are very similar. So first of all, I mean, assuming we have an infinite group, then if you take any unital C-star algebra and tensor it with a matrix algebra, and you look at this construction, take the Bernoulli shift, take the K-theory, then what this matrix algebra does is exactly it inverts n in the formula. Okay, so the reason why this is not obvious is that we have a shift action on this. I mean, we get some infinite tensor product of matrix algebras with a shift action, and what we prove is basically that this shift action is okay, not necessarily KK equivalent, but I mean, very close to being KK equivalent to a trivial action, so that you can just pull it out, and if you just have a tensor product with a UHF algebra, then you get this effect.
Could you explain this in the particular case when A is the complex numbers and G is the integers?
Right. So in this case, what you get is you have a UHF algebra with a shift action of the integers, and then then the K theory is just K theory of a circle, so if the C-star algebra of the integers, and then with n inverted. So you have Z adjoint 1 over n in degree 0 and Z adjoint 1 over n in degree 1.
But what's the relation between the algebras that you have on the left?
In the different lines, you mean?
Yeah, on the left in the two lines.
Yes.
I mean, you're like doing mn infinity like twice or something.
Right. So the point is, I mean, if the group is infinite, then it doesn't matter too much, because when you have kind of first you take an infinite tensor product without a group action, then you take an infinite tensor product with a group action, but it's it turns, I mean, the reason I put mn infinity in the second line is that I also want to have it for finite groups. And of course, for finite groups, if you just have a finite tensor product of matrix algebras, this does not do anything on K-theory. So this is, I kind of just want to enforce infiniteness. And so the statement is still that these things are okay. Now I have to be careful. I mean, the statement is still that these things are they're equivalent in the sense that I wrote down here. But if you have an a-T-menable group, then they are KKG equivalent, these actions. And in general, I mean we can prove that they are KKH equivalent for all finite subgroups, and then Baum-Connes tells us that we have this formula. But it's not so clear. I mean, especially when you don't look at K-theory, but really on the algebra level, it's not so clear what the precise relation is.
I mean, I have a question. Do you assume in the case where G is infinite, Baum-Connes for the group?
Yes. Maybe I should have written this also in the theorem. Right? Yes. So I put it in the first line of the slide. So in the title. But right. So I always assume Baum-Connes. Yes. So without Baum-Connes
in red, up there. Yeah.
Right. Yeah, but this is. I mean, this is at least important for the proof.
I mean, the general question I have is, I mean, do you need? I suppose, I mean, it's easier to make the blanket assumption that G satisfies Baum-Connes with all coefficients, but perhaps when what you actually use is that G satisfies Baum-Connes with the coefficients in some algebras that you use in the proof only, right?
Right. That's true.
And maybe in some cases you can describe this class in a reasonable way. I don't know, not in general,
but that's true. Yeah. So we don't need arbitrary coefficients. We just need the coefficients that we write down here, and some. Okay, so in this case, there's a third algebra in the background, which is the tensor product of the shift action and the trivial action on the UHF algebra. So there's a but yeah, so we only use it for explicit examples somehow, not in general. That's true. Yeah, but I will just I will just assume that it's yeah, but there are some things that can be simplified. It's true. Okay, but yeah, so this theorem tells us that we can get rid of matrix algebras, and then so this gives us the formula for general finite dimensional C-star algebras, because we can write every finite dimensional C-star algebra as a tensor product of a matrix algebra and something with co-prime ranks. So we can use the formula from before and just pull out the biggest matrix algebra that we can find. Okay, yeah, so this is finite dimensional algebras. So next I want to tell you what to do about AF algebras. And so what we tried to do in the beginning was we looked at this formula and we thought, okay, we have a nice decomposition for finite dimensional algebras, and if we have an AF algebra, maybe we can just write down the inductive limit, right, and calculate at every stage, and then take the inductive limit of these groups. And then it turns out these inductive limits can get very complicated, and the connecting maps can get very wild, even in not so difficult looking examples. And so I want to tell you about an abstract approach to this problem, and then give you some more abstract formula. And for this, sorry, I have another application before on the slide. I forgot. Kunst algebras, right? Okay, so before going to AF algebras, let me tell you about Kunst algebras. So what can you do about Kunst algebras? So the problem is that the inclusion of a unit does not split because you have torsion. You just have a torsion group in K0. And so we don't know how the K-theory looks in general, but we do know that if we tensor a Kunst algebra with a UHF algebra of the correct type, we just get 0 up to KK equivalence. And so there's a corollary that the K-theory, whatever it is, it will, after inverting n, we will get 0. And so this is okay. This is at least some structural statement that we can do. And now for finite groups, you can say a little bit more. So if you have a finite group and you have something like the Kunst algebra with finitely generated K-theory, then the K-theory of this cross product will again be finitely generated. Right, so then what you get as a result, so if you plug in the Kunst algebra and you say that n is a prime now, then you get some finitely generated group with a property that inverting p gives 0. And then and these groups always look like finite direct sums of z mod p to the k. So this is at least something we can say. But what exactly happens is incredibly difficult and also incredibly interesting. And so there's so Izumi has calculated these groups for when the group is a 2-element group. And in general, we don't know how these groups look like, even for finite cyclic groups.
The corollary simply says that this is a finite P group, a finite abelian P group, right?
Exactly. Yeah. So there's, So there's nothing new. It's just a reminder for people like me who are not so used to these terms in finite groups, in finite abelian groups, right? But okay, so I want to tell you about AF algebras, and for AF algebras, but by the way, how much time do I have? Like,
say 10 minutes.
10 minutes? Okay. Okay, I want to tell you about AF algebras. And so I'll quickly remind you about the orbit category. So you have a discrete group when you can form some category whose objects are just transitive proper G sets. So just G mod H with a finite subgroup H. Maps are equivariant maps. Okay, there's every equivariant map you can write down is just is a conjugate inclusion of groups. And then if you have a GC star algebra, I mean, with this picture, you can get a map from the K-theory of one cross product to the K-theory of the other cross product by a different group. The group element here is not unique. Yeah, there's some choice in this element G, but on K-theory groups, really, I mean, groups is important here. It gives you just the same map. And you can assemble this to a functor on the orbit category with values in graded abelian groups. And a little warning here. So this is this is a kind of naive approach, and so this should not be confused with the I mean, you can write down an assembly map for this, right? You have this functor, then you can take the co-limit and you get a map to the K-theory of the cross product, and this is not the same thing as the Baum-Connes assembly map. So this is just a warning. So this is kind of too naive because we do everything in a discrete setting, and we should do a homotopy co-limit in spectra instead. But I will just use this naive picture anyway, and it will work. Right. Okay, so here's the theorem. So assume you have now an infinite group satisfying Baum-Connes with coefficients, or with coefficients in a unital AF algebra. And now what I have to do, if you remember, for finite dimensional C-star algebras, we had to remember the largest matrix algebra that we can pull out of this matrix algebra. Yeah, we had to remember this. And so in the AF algebra case, what we have to remember is, I mean, also we kind of have to remember how many matrix algebras we can pull out. And the one way to encode this is to say, look at the unit in K-theory and look at its divisibility properties. Yeah, so we will just remember if a unit is divisible by some integer, and then we will remember all these integers. And now the statement is we don't get a concrete formula necessarily, but we always have a push-out diagram of this type. I mean, we can always write on this diagram, and the statement of a theorem is that this is a push-out. And so what we end up with is, so in the lower right corner, we have what we wanted to calculate, and in the upper right corner we have cross product by finite subgroups assembled together as a co-limit. And then we have some group C-star algebras of finite subgroups where we inverted the orders. I mean, all these integers that we remembered from the beginning, and also the one copy of a group C-star algebra. Also with these integers inverted. Right. And so, okay, so this is, I mean, I guess this is to be expected that, how complicated the K-theory of this cross product looks like necessarily depends on how complicated the structure of finite subgroups is in your group. But I mean, there's one example where this orbit category is really simple to understand, which is when we don't have any non-trivial finite subgroups. Yeah, so if we are torsion free, then this co-limit is really just the same thing as taking co-invariance. And so in this case, what we end up with is, I mean, we just get from the lower left corner, we get a copy of the K-theory of a group C-star algebra with the orders inverted. And then we have to split off the upper left corner, which is just just trivial. Right, and the upper right corner is just co-invariance of a K-theory of this tensor product, which can still be complicated to compute, but it's some formula. Okay, so this is AF algebras, and a similar strategy also works not only for AF algebras, but if you just tensor with irrationals. So this is some trick which is maybe not so complicated, but this has this really allows for many applications. So assume you have a unital stably finite C-star algebra. Then you at least get an injection on K-theory coming from the unit, so from the complex numbers to A. And then you can just tensor with irrationals and it will split. Yeah, because the irrationals are a field. So we can kind of force this splitting assumption by rationalization. And then the theorem is that so this is one version of the theorem. But in this case, if you also assume Baum-Connes with coefficients again, and you assume that A should also satisfy the UCT, then you can you can just rationalize everything, and you take some C-star algebra whose K-theory matches this co-kernel, and you get the same formula as before up to rationalization.
One little question. The reason you gave for the splitting of the map above was that the map, because of A being unital stable finite C-star algebra, the map before tensoring was injective.
Yes.
And then when you tensor, it splits because Q is a field.
Exactly.
Now, yeah, but why? I mean, you could say exactly the same thing for any field, such as a finite one.
That's true.
Does this make?
That's true. Okay. But let me think. Yes. Okay. I'm not too sure if the same result should hold. So what we are. Okay. I mean, I would have to look into the details again now, but I think the what we are using here is that I mean, tensoring with Q at the level of K-theory has the same effect as tensoring the algebra with the universal UHF algebra. And what we use here is this result earlier that if you tensor with M and infinity, and this holds for any UHF algebra, if you tensor with a UHF algebra, then the shift action on this UHF algebra is equivalent to the trivial action in a pseudo sense. And then we can kind of pull it, so we can replace the algebras, we can just tensor the algebras themselves with UHF algebras. And we get some some splitting in KK theory, really. And okay, with finite fields, I would have to think if, so it's at least not obvious, but maybe, I mean, this is a very nice comment. I mean, I haven't thought about finite fields, so maybe that's a similar
thing. It like goes in the opposite direction of inverting everything. I mean, you just
right. But I could imagine that this becomes more complicated because I mean, I guess what one would do then is maybe tensor with a Kunz algebra or something, but then
that the tensor with the Kunz algebra O(n + 1) is precisely taking the modern coefficient.
Right, but then it's not the same as tensoring with Z mod n, right? Or isn't there some?
No, it's like taking the difference between the fiber or the cofiber and.
Right. So I think it definitely becomes more complicated, but it's we haven't really thought about this. So there's thanks for the comment. It's a nice idea. Okay, maybe I should finish. So here's the same formula as I showed you for AF algebras, also works with rational coefficients under the same assumptions. So you have a unital stably finite C-star algebra satisfying the UCT, so that you get the splitting, and you assume Baum-Connes with coefficients. And a corollary to this, to either of these two theorems, is that if you have the Bernoulli shift action on a unital stably finite C-star algebra satisfying the UCT by a non-trivial finite group, this will not have the Rokhlin property. And okay, I will not go through the proof, but it's just show you that the proof is really short, and it can be checked with some K-theory computations. Okay, and I should end here. Thanks a lot.
Thank you very much for a very nice talk. any questions from the audience before? Because I have already asked a lot of them. I don't see any raised hands. I have a general question, which is probably more for Siegfried. So there are these corrections to the meaning of the cross product with a group in that, I mean, that you should take so that the Baum-Connes conjectural coefficients will hold if you take a different definition of the cross product. And then instead of the blanket assumption, the Baum-Connes conjectural coefficients holds for this holds, you could ask the Baum-Connes conjecture for this the variant of the Baum-Connes conjecture that is expected to hold for all coefficients holds, right? But I mean, I haven't seen articles which take this approach. No, if I don't know if there is anything that can be said along those lines. Perhaps what happens is you could that then you do not know how to compute the K-theory of the
right.
I don't know.
I mean, let's see. So a priori, there's no. So I think Siegfried already left. But okay, so a priori, there's no reason why we reduce cross product as special. So I think what we only need is that the cross product descends to a functor on KK theory. So this would be saying it's a correspondence functor in the language of Bus, Echterhoff, Willett, or I mean, all these works on these exotic cross products. And we would need that the Baum-Connes conjecture for the cross product we picked holds. So I think if you assume for example, the Baum-Connes conjecture for the minimal exact Morita compatible cross product, then it should the same results should hold with this cross product. Yeah, then it of course reduces questions about this cross product to other questions about this cross product. So yeah. But a priori, yeah, should work the same way. You just need, yeah, maybe you need that that the cross product functor descends to KK theory, but yeah.
Yeah, well, I mean, if it doesn't descend to KK theory, then I mean, there's no Baum-Connes.
I mean, what
you have another adapted version of KK.
Yeah, I mean, what you could do is you could still ask for everything to happen in E theory, where you don't need this extra assumption.
Exactness assumptions. Because
yes, and when you assume the UCT for E theory, I mean, so yeah, but I mean, yeah, I don't know how much one gains from this.
Okay, and a more a different kind of question. Why so? As you said, this colimit that you take is not the right thing to take. Because
right.
This is not. However, why does it work? I mean,
right. So this is really,
I mean,
yes. Why does it work? So the reason is, okay. Let me go back to or maybe let me go
to where the colimit.
Okay, let me go back to the formula where we had the colimit. Okay, so the reason is that if you look, I mean, what we do is we replace A by the unitization of some other C-star algebra, basically. So we replace A by some B plus. And then if you look at the cross product of this unitization, you will get, this can be split at least into two summands. So you have one thing is the unit, where the copy of the group C-star algebra of G comes from, and then the other one is, or maybe I should actually, it becomes more clear if I go back to the formula here, right? So if you look at this thing, so one copy is the group C-star algebra of the, it's just the group C-star algebra of the big group, and then the other summand is all these other finite subsets of G. So you get all finite tensor products of B, kind of, you get back. So if you look at this algebra, so the direct sum of all these finite tensor products of B, so this is a proper GC star algebra, but it's even proper over discrete space. And the thing is, if you have a GC star algebra which is proper over discrete space, then this naive assembly map will be an isomorphism, because the space is zero-dimensional and you don't need higher, you don't need any higher cells, so to say. So, but only for this very specific example, the naive assembly map works. So that's the reason.
Okay, so thank you very much.
Yeah, thanks a lot.
So if there aren't any more questions from the audience, I will stop the recording now.